Good morning. Homework number 6 is going to be due on Tuesday at 11 o'clock, and that includes questions from both Euler's equation, which we've covered the last 2 classes, and then the material that we're starting on today, Bernoulli's equation. Some relatively simple problems related to Bernoulli's equation is on homework 6, and so that's due on Tuesday. Today we're going to get into Bernoulli's equation, but first we're going to look at a brief video that touches on some of the ideas that we talked about in lab this week with laminar flow. Any questions related to the announcements? Yeah.
Next Tuesday, are we going in a more in-depth use of the Bernoulli's equation?
Yeah.
Okay.
Yeah. On homework 7, there's going to be additional Bernoulli's problems, and those will be a little bit more complicated than the ones that are in this first homework assignment. But today's class will be enough for you to solve the problems that are in homework 6. Okay, so this is kind of an interesting video that I stumbled across recently having to do with laminar flow. Is when we have a non-Newtonian fluid, which means that the viscosity changes as a function of the shear stress that's applied. And so a shear thickening fluid would be one like the cornstarch mixture that we looked at, where when you applied a shear stress, the viscosity went up. What he's saying is that that fluid, the cornstarch, is shear thinning, and so the viscosity, the faster he was moving the dial, the viscosity decreased. And there was some times when he was moving the dial slowly, sometimes he was moving it quickly, and so that the what little blurring of the die that did occurred at different rates depending on the speed that it was being rotated. But I guess what we saw in general was that this was laminar flow conditions where it wasn't mixing up the tracer die. Turbulence would have caused that die to be dispersed so that you couldn't unwind the spirals that were created. If there was a lot of turbulence, then that would have caused an advective mixing of the die. But in this case, it all stayed in one spot. He's got another video related to laminar flow that I may try and find like the best spot to show in class. But it shows a really interesting animation having to do with the velocity profile. And remember, in laminar flow, what we have is a nice parabolic velocity profile where let me pull up our slide that shows that, the parabolic velocity profile where at the center line of the pipe the velocity is the fastest, and here it is. So remember, in laminar flow conditions there isn't enough velocity and not enough energy for these layers to interact with each other. And he mentioned the phrase the no slip condition, so that at the edge of the pipe the velocity is 0, and even in a pipe where we have relatively fast moving liquid, there's going to be a zone, like some thin layer inside of the pipe where you have a laminar section where the velocity is low enough, even if in the entirety of the pipe cross section you don't have laminar everywhere, near the edges of the pipe it will be laminar. So I just thought that was kind of an interesting illustration of the specialty case of laminar flow. We didn't have quite perfect conditions in the lab, but I think in the Monday lab, the transition point that we visually observed was below 2,000, and in the Tuesday lab, it was above 2,000. So I guess maybe if we averaged the 2 days, we'd focus in pretty closely on those same 2,000, 4,000 breakpoints. All right, so what we're going to talk about now is Bernoulli's equation. And you'll remember that in Euler's equation we were using Euler's to predict a change in pressure in response to a local acceleration. In Bernoulli's equation we're going to be using a different approach. So in contrast to Euler's, where we were looking at local acceleration and how it changed the piezometric pressure between 2 points, in Bernoulli's equation we are looking at convective acceleration. And convective acceleration is non-uniform flow, where flow conditions are not steady with respect to position. And so when there's a convective acceleration, that too can change the pressure and elevation relationship in a way that isn't described by the hydrostatic equation. Remember, before we had any acceleration, the only tool that we had available for predicting the pressure was the hydrostatic equation. So here is Bernoulli's equation, one form of it. There's a couple of different ways to write it. But what it says is between 2 points, you have a pressure head term, an elevation head term, and a velocity head term. And between those 2 points, there's conservation between the sum of each of these three. And you can think of each of these three terms inside of the Bernoulli's equation as being energy. The first 2 terms is potential energy, and so pressure head and elevation head are related to potential energy, and then this third term, the velocity head, is kinetic energy. And so Bernoulli's equation talks about the exchange of different types of energy between 2 points. It has some pretty important assumptions that are built into the Bernoulli equation. And so there are 4 of them. And I think in the homework assignment I ask you to identify the 4 assumptions and explain them in your own words. So they are, first of all, that Bernoulli's equation is applied when you have steady flow conditions. So number 1, that means that the flow isn't changing over time. It's applied along a streamline. So if we look back at the equation here, it's between point 1 and point 2. So what that means is that you can only pick 2 points in the fluid that are connected with the streamline. And you'll remember that the streamlines that we've seen before were like the smoke that was going through a wind tunnel. Or the streamlines, let me go back earlier to show you the streamline slide. Okay, so here are some streamlines, these ones in light blue. It shows the direction of flow, and we can get a relative idea of when the velocity is changing as the streamlines get closer together. But you can only apply Bernoulli's equation along a single streamline. So we couldn't use that equation to predict, for example, the change in pressure between this point and the top streamline, because that's not connected by the same streamline. So that's the second assumption having to do with the Bernoulli equation, is that it's along a continuous streamline. And then the third assumption is it's for a fluid that's incompressible. And so the fluids that we're going to be dealing with this semester fall into 2 broad categories. There's liquids and gases. And of the 2, liquids are much closer to being incompressible. I mean, sometimes we'll call liquids incompressible, but really even liquids can be compressed a little bit with extremely high pressure. Like water, for instance, can be compressed. When we're talking about gigapascals, you can achieve a small percent reduction of the volume that water occupies. But more or less, water is pretty incompressible. So that's assumption number 3, is that the fluid is incompressible. And the reason why that's important is that Bernoulli's equation is going to be saying that there's some change in pressure that occurs when the velocity is adjusting. And if your fluid is changing in density, then there would be kind of a third degree of freedom there on why the pressure is changing. And so just to kind of take that uncertainty out of the mix, if you're dealing with an incompressible fluid, you're saying that as a fluid goes through a nozzle, for example, its density remains constant. So that's why we have the incompressible assumption with Bernoulli's equation, is just we assume that between 2 points the density of the fluid stays the same. And finally, this last assumption is that the fluid is inviscid. Anybody want to venture a guess of what an inviscid fluid is? That's right. And so an inviscid fluid is one that has no viscosity. Do you know of any fluids that have no viscosity? I don't. Yeah, there is no fluid that has no viscosity. There's some fluids that come pretty close, like fluids with a really low viscosity would be gases. The corn syrup that we just saw, that has a pretty high viscosity. Water has a lower viscosity than corn syrup, but then gases have an even, like many orders of magnitude, lower viscosity. And so if you look at these last two assumptions, in some ways there's a tension there, where Bernoulli's equation is more accurate the better you honor these assumptions. Now, the sad truth is there's actually no conditions where Bernoulli's equation applies perfectly, because there's no fluid that's both entirely incompressible and entirely inviscid. No fluid meets those two constraints. But we can sometimes get okay results with Bernoulli's equation. Like sometimes it does a pretty good job estimating, as long as we keep in mind what these restrictions are, and we only apply Bernoulli's equation in situations that are pretty close to honoring these restrictions. And so for the first, an incompressible fluid, I already mentioned to you that of the gases versus liquids, liquids are better in terms of incompressible. But then when it comes to inviscid fluids, gases are closer to being inviscid than liquids are. So when you see mistakes in how well Bernoulli's equation predicts what you actually observe in the lab, those mistakes, or Bernoulli's shortcoming as a model, are going to mostly stem from the fact that your fluid isn't incompressible and it's not inviscid. Now the reason why that inviscid fluid assumption is there is that an inviscid fluid is one that's not going to experience any pressure change due to energy losses. There isn't any pipe friction for an inviscid fluid. And Bernoulli's equation, these two terms, the amount of energy at 1 and the amount of energy at 2, this Bernoulli's equation doesn't account for any losses between the 2 points due to pipe friction. And so an inviscid fluid is going to be one that experiences less or no energy loss due to pipe friction. And so the more viscosity you've got in the fluid, or the faster the velocity, just in any way, anything that contributes to energy loss is going to make Bernoulli's equation less accurate as a model. So we'll continue to come back to these 4 assumptions as we work some examples, and on Tuesday when we look at applications of the Bernoulli's equation with a pitot tube. But just keep in mind that no model is perfect at describing reality. They're just always approximations. And so an engineering model, whether it's an equation or whether it is an actual physical model or a numerical model that's set up in a computer, no model is going to be perfect at describing reality, but there are a lot of times when the Bernoulli's equation is close enough. Yeah.
So using the Bernoulli's equation, we can make the assumption that the acceleration of the fluid is constant. Is that a safe assumption or not? Because as I understand, there's a steady flow, so the velocity must be...
Remember, there's 2 kinds of acceleration.
Right. Local.
We assume that the local acceleration is 0, but there's a convective acceleration that's not constant, because if we have a nozzle, the convective acceleration will be different in different locations.
Okay.
All right. Now, I've mentioned the word models a couple of times today, and a model is just a representation of a system. It's a way to understand something that's more complicated or that's bigger by constructing something that's simpler or smaller. So here is a physical model of an aircraft, and this is a 747, and this is the model of a 747 in a wind tunnel. And so the reason why the model would be used would be maybe they're going to make some changes to the wing, or try a new engine casing, or just whatever change or adjustments they want to make. It's much cheaper to make those small iterative adjustments to a small scale model than it is to a full-size prototype. And so it allows for you to look at changes and predict behavior in the real world with just a simpler analogy of that full-size system. So those are physical models. Bernoulli's equation is a model of how things how fluids behave in the real world. And the Bernoulli's equation is considered a fundamental model, where the units on both sides of the equation are equal, and we don't have any sort of correction factors built into Bernoulli's equation. In contrast to that, an empirical model is one that's just constructed based on many observations of gathered data. And so, for instance, we might have an equation that predicts the range of an aircraft based on how much fuel is available and the weight of the aircraft. But then we have these strange correction factors, or like maybe unit adjustment curve fitting parameters. And it's simply that we had a bunch of data, and you could create an empirical model like this by just putting data into Excel and have it do the best fit regression analysis. That's an example of a regression giving you an empirical model. And so the units of the terms on the right-hand side don't necessarily work out to be the same as the units on the left-hand side. It's not dimensionally homogeneous in many cases for an empirical model. When we apply a model, there are boundaries that specify the extent that the system is being considered. And in Chapter 5, we'll spend a lot of time talking about how to set the boundaries by considering the control volume. That is just sort of the volume in which the object of interest is placed. And so the control volume for this physical model of a 747 would be the interior of the wind tunnel, for example. The variables in a model are the things that change over time, like the velocity of the wind, the pressure of the gas, the elevation of the plane. Those are the variables that do change, but then there are also parameters that are the physical system constants that don't change, like gravitational acceleration, the density of water at a certain temperature, the viscosity of water at a certain temperature. Those are parameters. So later in the semester we'll come back to the idea of engineering models, and we'll do something that's called dimensional analysis, and it's kind of the study of how units and how variables can be used to create new equations, and how to design experiments so that you're gathering all the data that you need in order to create empirical models. Okay, so back to Bernoulli's equation. Bernoulli's equation says that along a streamline, when we have steady flow for an incompressible, inviscid fluid, that there is conservation of the piezometric pressure and the kinetic pressure. And earlier I mentioned that we can think of the two main terms on each side of the Bernoulli's equation as being like potential energy and kinetic energy. Well, here the Bernoulli's equation is written a little bit differently from the first time that I showed you. The first time that I showed you, each of these terms was divided by gamma compared to what's shown here. And so it was pressure 1 divided by gamma plus Z1 plus V1 squared divided by 2G. So it's just, the difference here is that sometimes you'll be solving for an unknown pressure, in which case it maybe is most convenient to start with this form of Bernoulli's equation. In other cases, you'll be solving for the elevation, and maybe the other form of Bernoulli's equation is most convenient. But what it says is between 2 points that there is complete conservation in the amount of energy that's available at the 2 points. And it's just that the energy changes form. So at one point, maybe you'll have a lot of pressure, but then if the velocity increases at the next point compared to the first, then the pressure would have to go down. So here are the two terms, the two different ways of writing Bernoulli's equation. In hydraulic engineering next semester, I'll almost exclusively write Bernoulli's equation like this. This is the term that in hydraulic design we use because a lot of the energy loss parameters, where we actually now no longer have to assume that the fluid is inviscid, a lot of the energy loss formulas will solve for head losses in terms of meters. And so then just combining it with this version of the formula is most convenient. So here's a case of where we would use Bernoulli's equation. This is showing non-uniform flow where there's a convective acceleration. And what we could use it for is to predict how this velocity change is affecting the pressure. So our convention typically is to let location 1 be the upstream location and location 2 be the downstream location? It doesn't strictly matter quite yet, but it will when we do start accounting for energy losses. So it's just good to get in the habit of saying that 1 is upstream, 2 is downstream in the direction of flow. What this formula will allow you to do is it'll allow you to say, if you know the pressure at 1 and you know how the velocity is changing, then that allows you to predict the pressure at 2. So in this specific case, you'll notice that the velocity is going up. So if the velocity is increasing, and if we're considering 2 points that are on the same horizontal elevation, so Z1 and Z2 are equal, then how would the pressure be affected by the fact that the velocity is going up? What's happening to the pressure? If V is going up, what happens to P? Decreases. It has to. Like if you look at this equation, it says, all right, V2 is higher, so if all these things are going to add up, like if pressure, elevation, and velocity terms are going to add up and be equal between the 2 points, if the velocity at 2 is higher, so this term is now bigger than it was before, that energy has to come from somewhere. The energy required to have additional velocity at 2 is going to come at the expense of the energy that was tied up as pressure. And so now at location 2, the pressure is going to be lower. That's what Bernoulli's equation says. It tells us how much the pressure changes as a result of these velocity changes. Okay, so to get some practice with that, just starting in the most simple case, I'd like you to try and substitute into the Bernoulli's equation these two locations, where at 1 we know the velocity is 5.5, at 2 we know the velocity is 0.6358, and the given pressure is known at location 1. We want to know the pressure at location 2. Go ahead and assume that we're at the center of the pipe for both of these locations of interest. So the elevation Z1 equals Z2.
If we find out that it's weak, we're gonna
All right, so the pressure at 1 is 400. We're trying to find the pressure at 2. We can rearrange the equation to solve for P2. It's just going to be the pressure at 1 plus the elevation at 1 minus the elevation, plus the velocity head term at 1 minus the velocity head term at 2. So we should get 415 kilopascals. You'll note that I wrote like the intermediate quantities here, and the units there are going to be meters. And so the pressure head, there's 40.775 meters of pressure head. So at 1, most of the energy is in the pressure head. Even though the velocity is moving very fast, 5.5 meters per second is very fast moving water, there still isn't very much energy tied up in that kinetic term. And so the majority of the energy in the water is as pressure compared to how much is there as velocity. And so the velocity at 2 has slowed down a lot. And so since there's less energy in the velocity at 2, then what that means is it frees up more energy to go into the pressure at 2. So it's good to be able to calculate the amount of pressure at 2, but also think about why did it go up. It's just that some of the energy that existed as kinetic energy at 1 is now being transferred into additional pressure at 2. Any question about that? All right. So let's consider the similar shape, but in this case the nozzle is decreasing in diameter, so that if we had a certain velocity that was going in, it's going to be faster by the time it comes down to this discharge side of it. And let's talk about why that is. Let's consider this shape, this system, is full of water, some non-compressible fluid. And so what that means is that there's no capacity to store water inside of this object if it's already full. Okay, so it means you can't put in a liter of water and have nothing come out. What it means is that any additional fluid that goes into the system has to come out of the system with an equal volume. So a liter in is going to cause a liter out, because if you add an additional liter of water, then that's going to push the same volume out, since it's not going to be compressing and it's not going to be stored. Just in equals out in this case. So that being the case, if we know the diameter at 1 and we know the diameter at 2, then from the diameter we can calculate the cross-sectional area, both in the inlet and at the outlet. So we've got A1 and A2. And we know that the flow rate is the cross-sectional area multiplied by the velocity. So one of the problems that you have in the homework requires you to know that A1 V1 equals A2 V2. And what you're really saying with this formula is that the flow rate in and the flow rate out are equal. And so Q1 equals Q2 is just saying that if you have a certain volume of water entering this system where there's no compression and there's no storage, that you're going to have the same amount coming out. It's just that sometimes it's going to be coming out at a different velocity. The inflow here will have a relatively low velocity over a large cross-sectional area, whereas at the outlet, since there's a small cross-sectional area, there's going to be a higher velocity. So the previous example that you just worked, the pressure went up because the velocity decreased. What about here? What would happen to the pressure in this transition?
At position 2, the pressure would be a lot lower than it was in position 1.
That's right. So the pressure is going to decrease through this nozzle. And keep in mind the idea of vapor pressure. When we started the semester talking about fluid properties, one of the things we talked about was each fluid has a tendency to go into the vapor phase. And fluids like alcohol have a higher vapor pressure than water, and what that means is that they evaporate faster and that they're much closer to boiling at ambient temperatures. Well, another way to get things to boil besides raising their temperature is to reduce the pressure that surrounds them. And so you'll remember we watched a video of water in a vacuum bell that was boiling, simply because the pressure that surrounded that water decreased. So another way of having low pressure, besides like a vacuum bell, is in a transition like this, where you suddenly have very fast-moving fluid. That can cause the pressure to decrease to the point where the liquid can potentially begin to boil or cavitate. So something that we'll look at later in hydraulic engineering is preventing cavitation in cases where suddenly the velocity is much higher because of a cross-sectional area decreasing like this. So this is just the general idea that A1 V1 equals A2 V2, but specifically for diameters decreasing, that causes an increase in velocity, a decrease in pressure. There's a risk of cavitation there. All right, so let's have this be one of these nozzles that are contracting. And this is a little bit more complicated because what we're doing is we're using a differential manometer to measure a pressure change between points. And there's 3 points that we're interested in the direction of flow. There's air that's traveling through this nozzle, and so at 1 you can see that the air has relatively low velocity, and at 2 the velocity is higher because the diameter is decreased and the area is different. In this example, what we're going to say is that the area at 1 is twice the area at 2. So the area, another way of thinking of it, is the area at 2 is half of the area at 1 because the diameter decreased. So therefore, V2 is twice V1. So if the area is double here, then that means the velocity is going to be half. Or if the area here is half, that means the velocity is going to be double. Okay, so we have a relationship that tells us how the velocity is changing, and we know the density of the fluid, it's air, and we're going to assume that this air isn't changing in density as it moves through the duct. What we want to know is what's the velocity at 2. And even though we don't know the absolute pressure, we're still going to be able to calculate the absolute velocity at location 2, because this differential manometer tells us the pressure change between 2 points. So we're going to combine Bernoulli's equation also with the manometer equation, the hydrostatic equation, because inside of this differential manometer the conditions are static. And so we have the pressure at 1, the pressure at 2, and you'll notice location 2 is just before the air reaches the differential manometer. And if we zoom in on the opening of that differential manometer, what it shows is that we have a streamline that suddenly stops at a stagnation point. And so the streamline, the air is moving, and at location 2, which is just to the left of the opening, the air has velocity. But then when the air bumps into the opening of this tube, this differential manometer, inside of the tube, conditions are stagnant. We have static conditions where there's no fluid moving at all inside of the tube. And so the pressure is even a little bit higher than it ordinarily would be, because all of the energy that existed as velocity head at 2 has simultaneously been changed into additional pressure here at location T. So my suggestion for finding the velocity at 2 is we're going to use Bernoulli's equation, and we're going to have the elevations are all going to be equal. And so we know Z1 is equal to Z2 is equal to Z sub T. Here at location T inside of the tube, we know that the elevation is the same as those other 2 points. The manometer equation is going to tell us the change in pressure between the tube and location 1. So what I'm going to do is I'm going to pause for a moment and give you some time to calculate the change in pressure, and then see if you can substitute that into Bernoulli's equation in order to find V at location 2. And so you can find the velocity at location 1 and the velocity at location 2 both, since we know this ratio of their respective velocities. I want to mention something about the differential manometer. We're going to assume that the pressure of the gas inside the manometer is constant everywhere inside of the stagnation tube. That the pressure changes when we have the water part of it, because water has a relatively high density. But inside of the air portion of the differential manometer, the pressure isn't changing, for example, just inside the tube compared to that interface. And so when we apply the hydrostatic equation through the manometer, what we say is the pressure at 1 is the same thing as the pressure at that interface between the gas and the water, because pressure doesn't change much through air. You know, like if you go a meter up or down through air, it's not like your ears are popping. But Through water, which has a much higher density, the pressure does change significantly through this delta of 10 centimeters. So in other words, here's the nozzle, and we have here at location 1, I'm saying that let's take the, if this is P1, this is also P1. The pressure is the same between the two locations. But then this ties back in, and we have a deflection. This side's lower here. So the 10 centimeters. This I'm going to call the pressure inside the tube. And what we mean is the tube that's receiving this stagnating streamline. And so on the inside here, P sub T in the tube is the same at the bottom and through all of the gas inside of the stagnation tube. But the pressure inside the tube is not the same as the pressure at 2. And think about it logically, the pressure between here, where the gas still has velocity, is going to be different than the pressure inside the tube. Because all of the velocity that the wind had, once it bumps inside of the tube, that kinetic energy is going to be transferred into additional potential energy in the form of extra pressure. So there's going to be more pressure inside of the tube than there is just outside of it at location 2. In any case, I just wanted to explain the clarifying thing that we're saying the pressure of the gas inside, everywhere inside of that differential manometer that we have a gas, the pressure is the same. So how come we can't apply Bernoulli's equation directly from 1 to 2? Well, at location 2, there's too many unknowns to do that. We don't know the velocity at location 2, and we don't know the pressure. But we can apply Bernoulli's equation between 1 and T, because the situation is a little bit simpler at location T inside of that tube than it is at location 2. Because at location T, there's no velocity. And so that's eliminated one of the unknowns that we had. Remember, at location 2, we didn't know the velocity, and we also didn't know the pressure. But at location T, we know the velocity is 0, and we know the change in pressure between 1 and T. So in other words, this delta P that we calculate with the manometer equation, delta P is P sub T minus P1. So if we rearrange the Bernoulli equation to have P sub T minus P1, then we can use the change in pressure that we calculated with the manometer equation. Okay, so we've got two different fluids there. We've got air that's passing through the nozzle. Boy, that's a nice sketch. You guys are so lucky to have me as a professor. Yeah. The air density, we need to calculate the unit weight from the given air density. We need to calculate the unit weight. No, we already know for water. Okay, so the basic principle is that there's conservation between 1, 2, and T. It's just that the energy is changing form between especially 2 and T, where the velocity stops entirely. And so at 1, the energy is the pressure head and the elevation head. But at T, there is no, did I call this elevation head? It's the velocity head. At T, it's only just the pressure head. The elevation between the 2 points is the same, and there's no velocity at location T. So the substitution into the Bernoulli equation from above, where we calculate the change in pressure is 981 pascals, then we can put that onto the left-hand side of the Bernoulli equation and solve for V1. And once we know the velocity at 1, the problem is asking for the velocity at 2, and we know that it's double, because in the problem statement it says the area at 2 is half of the area at 1, so the velocity will be double. Okay, so back to this solution. Sometimes combining two relatively simple ideas together can make things a little bit complicated, but that's what we did here. We combined the manometer equation and the Bernoulli equation. And the idea of differential pressure measurements is going to continue to be important when we talk about pitot tubes in class on Tuesday. But are there any questions on this example? So if V1 is 40.4 meters per second, then V2 is 80.8 meters per second. Okay, the homework assignment you're working on right now is due on Tuesday by 11 o'clock. If you have any questions, feel free to stop by or send me an email. Have a good one.
So what's the lab going to be about next